Hi everybody. As we are starting to learn, a lot of physics is about determining mathematical relationships between different quantities. In this tutorial, we'll be giving names to several types of relationships that are very important and that keep happening again and again in the physics phenomena that we're going to be seeing. I'm going to just kind of put everything out there all at once here on this slide and go through the basic types of relationships that we'll be considering in this tutorial. There are really four different ones that show up a lot. The names of the relationships are given over here on the right-hand side. We have direct proportions, we'll have inverse proportions, we'll have power curves, and we'll have exponential relations. Okay, and these names have very specific meanings. And when you talk about a direct proportion, you're talking about a relationship that has a specific type of a formula, and it's going to have a graph that has a specific type of a shape. So let's talk about direct proportions first, because this is the most important type of relationship that we'll see this year. You probably know the most about direct proportions already as well. So a direct proportion is a relationship given by the formula y equals mx plus b. M is slope, b is the y-intercept, and your variables are y and x. When you graph a direct proportion, you get a line. So over here in the graph, you can see an example of a line that has a positive slope. It's shown by the light blue diamonds. You also have a line that can have a negative slope. It's given by the dark blue squares. Both of these relationships are considered to be direct proportions. And the idea is that for every step forwards that you take in x, y will either go up or down by a fixed amount. And that's how you get a straight line. Okay, and we'll take a look at some examples of that. Okay. In fact, why don't we go and look at one right now. Here's an example where you've got some data in the table here, and values for x are listed on the left side, values for y are listed on the right side. Okay, and the question is, okay, what's the relationship here? Well, x is going up by nice even steps. The steps are 1,000. Okay. Turns out that y is also going up by nice even steps. Can you tell what the step is? It's 500. So every time x increases by 1,000, y always increases by 500. That is the signature, that's the characteristic of a direct proportion. Okay? If we plotted this, we would see a line. The line would have a positive slope. That means it's sloping up. There we go. And take a moment and think about what the slope would actually be for this graph. Think about it. Every time you move forward by 1,000, you're moving up by 500. That would correspond to a slope of 0.5, or 1/2. And of course that would be a positive value. So simply by looking at this data, you can tell that you've got a direct proportion, and you know that the slope is positive and it has a certain value. Okay, so a very important type of relationship. Now let's have a look at this data. This data is different. Every time x increases by 1, y decreases. But notice that y, let's take a look at these values. 120,000, 100,000, 80,000, 60,000, 40,000. In other words, y is always decreasing by the same amount. It's always decreasing by 20,000. For that reason, this data is representing a direct proportion. Okay? Now, sometimes students will look at that and they'll say, well, that's an inverse proportion because y is decreasing as x increases. But that is not the case here, because y is decreasing by a constant amount every time x increases by a set amount. So if you were to graph this data, and I encourage you to do that, you would actually get a line, but in this case the line would have a negative slope. Okay, because y is decreasing by that certain amount. Now, can you tell what the slope would be without using the calculator? Every time x increases by 1, y decreases by 20,000. That corresponds to a slope of negative 20,000. Okay, and that's what we would get for this. So this is a direct proportion. All right, so I'm going to back up to our chart. Here we go. And we've just seen basically those two graphs that I showed here, although with different numbers. Now, the second relationship that's very important to us is going to be an inverse proportion. In an inverse proportion, we say that y is inversely proportional to x. It is defined by the formula y equals a constant divided by x. When you graph it, graphing y versus x will give you a hyperbola, and that's the shape that's shown in this box here. Now, a hyperbola is a curve, and a hyperbola never crosses the x-axis or the y-axis. You can prove that to yourself by plugging in very large values for x, okay? And you'll notice that y never quite reaches 0. So you have an asymptote along the x-axis. If you plug in very small values for x, what will happen is that y will become very large, and it will approach infinity. And it's not defined at x equals 0 because that's dividing by 0. So that's what a hyperbola is. A hyperbola has asymptotes. Let's take a look at what a hyperbola would look like if we see a data table. Okay, so here's some data where we have, again, x increasing in nice even steps, 1, 2, 3, 4, 5, and we see that y is decreasing. So the first thing you should look for here is to see, is y decreasing in equal steps? And I hope you can see that it's not, because from here to here, y decreases by 60,000. But then, in the next step, it decreases by a lesser amount, only by 20,000. Going from 40 to 30,000, y is only decreased by 10,000. And so y is decreasing by smaller and smaller amounts. And that's an indication that what we're seeing here is an inverse proportion. Okay. In fact, another way to look at this would be to say, would be to compare any one of these data points to the very first one. Let's take, for example, x equals 3. At x equals 3, y is equal to 40,000. Let's compare that to x equals 1, y is equal to 120,000. In other words, when you triple x, and you go from x equals 1 to x equals 3, that's tripling it, what happens to y is that y decreases by going to 1/3 of its original value. So it goes from 120,000 to 40,000. Okay. As another example, what happens if we double x? So, for example, go from x equals 2 to x equals 4. What happens to y is that it goes from 60,000 to 30,000. That's a decrease of 1/2, a factor of 1/2. And that makes certain that this is an inverse proportion, the fact that those types of proportionalities exist. And so we know that when you graph this, you would get hyperbola. Okay. So that's an inverse proportion. Let's go back to the third type of relation, which is called a power curve. The power curve is given by the formula y equals kx squared. In fact, in general, it doesn't have to be a square. It could be any integer here, any number, but we're going to really be dealing with squares in this course, so we'll just deal with this one. When you have this type of formula, you say that y is directly proportional to x squared. Notice that you're not saying that y is directly proportional to x, but to x squared, and then that makes sense. When you graph this relationship, you see this type of a shape. That's a parabola. A parabola is a curve. The parabola does not have asymptotes. In other words, a parabola just keeps growing in the x and y directions as given by the formula. Okay. Now, a parabola a power curve is an interesting relationship because it says that y is changing especially fast with respect to x because x is squared. Okay, so y is strongly dependent on the value of x. Let's see an example of what this would look like. Okay. Alright, so if you take a look at this data, x here goes 10, 20, 30, 40, 50, etc. And y is increasing. But y is increasing fast. It's going from 100 to 400, and then to 900, then to 16, and then to 2500. It's growing very quickly. And in fact, you might recognize these numbers as squares. 10 squared is 100, 20 squared is 400, 30 squared is 900, etc., etc. And so we see this kind of this dependence on the square of x. Okay, this relationship shows up notably in the formula for kinetic energy. It turns out that kinetic energy is directly proportional to the square of velocity. So as you go faster and faster in your car, the kinetic energy of your car grows very rapidly, much more rapidly than you might think. And this is why it's important not to speed, because it becomes more and more difficult to brake, depending on your kinetic energy. Okay, so, whoops, went too far. That's our power curve. Almost everything we will do this whole year will be either direct proportion, an inverse proportion, or a power curve. The last relationship here is something which shows up in physics and chemistry. It probably won't show up for us very much this year, but I'd like to at least state it, because oftentimes students like to use the word exponential when it's not quite the right word to use, and I want to make sure that you understand it. An exponential relation is a relationship in which x is in the exponent of some constant. So formula-wise, these are two examples of exponential relations. It can either be a positive exponential, such as given by the solid squares, or it can be an exponential decay with a negative x in the exponent, and that's given by the solid triangles. Now, a positive exponential curve looks a lot like a parabola, but in fact it's not. It has different behavior, and the relationship itself is quite different than what we have above. So don't confuse power curves with exponential relations. A decaying exponential is oftentimes confused with a hyperbola, or an inverse relationship. But again, it's not the same thing, and you know, the graph is different and the formulas are different. So kind of be on the lookout for that, and be very careful in what you call exponential, because we won't be seeing that too often. So that's the end of the tutorial here. I just wanted to map out the four types of relationships that are probably the most important to us. Of the four, it's really the first three that we'll be seeing a lot of. So this should help us as we learn to discover more about relationships in physics. And I hope you had fun. I will see you later.